Okay. So we'll get going in a minute. I'm going to type some instructions into the chat window and then I'll say them aloud as well. That will kind of describe how we're going to operate the webinar today, and then we'll get started. Okay, great. Welcome everybody to another IRSIG webinar. I will be moderating the webinar today. My name is Meredith McGregor. I'm one of the co-chairs of our IR Science Interest Group Leadership Council. And outside of that, I am an assistant professor at the University of Colorado Boulder. So I typed these instructions into the chat window, but just to go over them audibly as well. Please use the chat window in Zoom for basically everything. That means submit your questions for the speaker via the chat window. It would be great if you can submit your questions as they come up. Then our speaker can either choose to answer them during the talk, or we'll have a Q&A session at the end where we'll save questions and we'll ask them to the speaker at that point. You can also use the chat window to submit additional feedback or comments or questions that you have for our IRSIG Leadership Council. We'll save those until the very end of the hour if any of them come up. And if we run out of time, then I will be sure to send you an email response afterwards. Of course, report any technical difficulties, audio problems, issues with Zoom through the chat window as well. And the last important piece of information is that this webinar is recorded and will be available to view later on our webinar webpage. And we have a new webpage. That change happened within the last month, so you can find the link to our new webpage at the bottom of the chat window there. And then if you are unfamiliar with Zoom, which is probably unlikely at this point, you can get the chat window open by going to the bottom of your Zoom screen and clicking on the thing that says chat. And that will bring open the chat window for you to use to ask questions and such. Okay, with that, I am excited to welcome our speaker for today, Stacey Alberts. Stacey is also a recent member of our IRSIG Leadership Council. She is research faculty at Stewart Observatory at the University of Arizona. Stacey got her PhD from the University of Massachusetts Amherst and then started as a postdoc at Stewart, where she's also a member of the JWST MIRI instrument team and then the JWST MIRI and NIRCam science teams there. And today, Stacey's going to be telling us about measuring the total infrared light in high redshift galaxy clusters. And with that, Stacey, you can take it away.
All right. Thank you very much for the introduction, and happy Tuesday to everybody. I'm excited to be here to talk to the IRSIG about our recent work looking at high redshift galaxy clusters. Oops. Okay. So most of what I'm going to be talking about today, the work and plots that I'll be showing was in this paper submitted earlier this summer to MinROS. It's up in archive already at this address if you're interested in more details. And of course, it is a joint work effort, all the hard work by these people that are listed here. So a brief outline of my talk. I'm going to have a quick introduction talking a little bit about clusters and protoclusters, then a little bit about our cluster sample and some of the considerations that went into the method of our total light stacking techniques to get at the total cluster emission. Then on our results, the total light radial profiles and integrated cluster emission and what we can learn from them. And then just a brief mention of some of our future work that is coming up. All right, so massive galaxy clusters represent the extreme case of a galaxy's property and its destiny being tied to its local environment. So of course, in the nearby universe, we see that galaxies that reside in massive clusters are largely populated by red and dead galaxies. So this means that environmental mechanisms are preferentially shutting down star formation in these overdensities. And this is illustrated really nicely by the local Coma supercluster region, which hosts a wide range of environments. So we can take the galaxies in this region and we can split them into voids, filaments, groups, and of course the cluster itself. And if we look at the star forming fraction, even broken down by high mass, which is the red points, and low mass, which is the blue points, we see that the star forming fraction decreases steadily with increasing local galaxy density. And by the time we get into the coma cluster itself, we of course see that most of the star formation has shut down. So these local clusters are a really nice way to study the end game of environmental effects. And of course, we can get a really close look at some of the effects that might be still happening in the outskirts of clusters. So over here, we have an example of a star-forming galaxy that's falling into a local cluster, and you can see one of these environmental effects. You can see the ram pressure stripped tail of material coming off of the galaxy. This is actually one of our JWST GTO targets. So if you're interested in ram pressure stripping, stay tuned. We're really excited to see more details about what this process is doing. But of course, we want to understand the entire history of clusters and even the protoclusters, which are the still forming clusters at higher redshift. So studies have been in the last years and decades have been pushing to higher redshifts to look at massive virialized clusters above redshift 1, and then also to look at what protoclusters are doing above redshift 2 or so. And so here, okay, I should mention that by protocluster, I mean an more dense system that is prior to relaxation and virialization. So it doesn't yet have a developed intracluster medium. It's kind of, so that's kind of the definition of protocluster. In this particular plot from a recent simulation, we're looking at protoclusters and then the most massive halo in the protocluster called the protocluster core. And this plot is showing you the fraction of cosmic star formation rate density contributed by galaxies in these systems as a function of time. So the local massive clusters that we were just talking about are of course down here, and as we were just talking about there, mostly quenched populations are not contributing much to the cosmic star formation rate density. But if you go back over here towards the epoch of reionization, we're starting to get the idea that up to 40% of the cosmic star formation rate density might be contributed by galaxies in these protocluster systems. So if you're interested in high redshift studies in reionization, the galaxies that are in these systems might be really important to what's going on. I also wanted to note that these protocluster systems are taking up something like 5% of the cosmic volume at these high redshifts. So if you're interested in the topological features of the cosmic web in the early universe, these are going to play a role as well. So from these same simulations, we can kind of put together what we think is the roadmap for how these protoclusters evolve into cluster systems and into the massive cluster systems that are quenched that we see today. And so at redshifts greater than 5 to 10 or so, we think that the most massive halos in the universe start to grow by kind of inside out growth with infalling and a little bit of quenching in the center, kind of on the 10 to the 12 solar mass scale. And then when they get down to redshifts about 2 to 5 or so, they start to accrete more massive halos. You might have a somewhat quenched central halo here, and then you get a lot of these little halos in a region of very extended star formation that takes up quite a big area on the sky. And then when this process is kind of gets to the point where we're going to transition to more virialized clusters that we know in the more local universe, we go back to kind of an inside-out growth picture where you have your now massive halo in the center, and you're still going to accrete galaxies and groups, but you're going to do a more inside-out growth where your virialized halo is going to grow by accreting things that are experiencing pre-processing, and they're being processed as they infall into the massive halo in the center. So observationally, we know, of course, a lot about what's happened below redshift 1 with these virialized systems and the pre-processing that grows them. And we're just starting to look at the more protocluster systems and starting to see these extended regions of star formation at redshifts greater than 2 or so. And we're finding that these extended regions of star formation are very dusty, which is kind of interesting. But of course, there's a lot more details to learn about how this entire process happens, and particularly the transition between this epoch of extended star formation and then where we get down to the more virialized, relaxed clusters. So that's the region that the epoch that I'm going to focus on today. We're going to look at clusters between redshifts 0.5 and 1.5 with 1.5 being where we think kind of this transition between these more protoclustery systems and these more relaxed systems is happening. So if you were going to make a naive guess at how this transition happens, it wouldn't be unreasonable to think that star formation is shutting down somewhere between these, when you have this period of extended dusty star formation that's very starbursty, a lot of mass grows all at once. And then by the time you get to, things are starting to relax and virialize, you might think that all the star formation is already shut down. And this was actually supported by some early studies. So this is a look at optical colors of cluster galaxies up to redshift 1.5 or so. And these lines here are showing you pathways of evolution where you have a burst of star formation at a high formation redshift, so there's 4 and 5, and then followed by largely passive evolution after that burst dies down. And you can see that the optical colors of these cluster galaxies are kind of following these pathways where you had an early burst of star formation and then passive evolution afterwards. So it was kind of looking like, most of the action was happening in the protocluster phase, and then once you get to the virialized phase of massive clusters, things are pretty well on their way to being passive populations. But recent studies have found that this is maybe a little bit more complicated picture, actually, is what's happening. So this is a recent study of massive clusters where they looked at the environmental quenching efficiency. So this is the fraction of galaxies and clusters that are passive that would have been star forming if they were in the field. And they determined this by using the UVJ selection. And you can see here at redshift 1, like we've been talking about, the quenching efficiency is rather high. Populations in the cluster are very well quenched, even a little bit above redshift 1. But when you get up to redshift 1.5 or so, the environmental quenching efficiency of these galaxies in these massive clusters is suddenly much less efficient. So we're actually looking at an epoch where there is quite a bit of activity going on, even though we're kind of in a more cluster phase rather than a protocluster phase. So if you wanted to go out and look for these galaxies, you might take a cue from your field and wonder if they are pretty dusty. So this is a plot showing the total star formation rate, the total star formation activity in field galaxies as a function of cosmic time. And what it's showing you here is that, more normal galaxies are kind of dominating here. But when you get up to the cosmic noon type era above redshift 1 or so, the dusty high star formation rate galaxies start to dominate. So if you want to go out and look for the galaxies that are actually doing the activity that haven't been quenched, you might want to look at dusty star formation rate indicators. So that is what we did. And this is actually the sample that I'm going to tell you about a little bit later, but we went and we got deep MIPS and Spitzer MIPS and Herschel PAX data for a set of massive virialized clusters. And we looked at the top 2 plots here are the field relative fraction of star-forming galaxies with infrared indicators of star formation rates as a function of projected radius. And we're kind of using the farthest radius point here that we have as kind of our normalization for where the environmental effects are tapering off. And you can see for the red points, which are our highest redshift bin, greater than redshift 1.4 or so, we see that the environmental effects that are quenching the star formation, turning it off at lower redshifts is no longer really that effective. In fact, with the MIPS data, we saw a little bit of a rise into the cluster centers. With the PAX data, we saw that it was consistent with mostly being flat, whereas when you go to lower redshift, you see this dip in the star forming fraction. If we look down here at the specific star formation rates of these galaxies, again, we see that the specific star formation rate of these cluster galaxies is pretty flat until you go down a little bit in redshift. There's not actually that much time between these 2 bins, but you immediately start to see the quenching effects kick in. So this is indicating that the star forming populations of these clusters particularly the dusty star forming populations, are kind of pretty rapidly undergoing a transition from ineffective environmental quenching to more effective environmental quenching. And I wanted to note down here that all of this is looking at massive galaxies. So this is log mass greater than 10 in massive clusters greater than 10 to the 14 solar mass. And just to drive this point home a little bit more, we looked at the total star formation rate per halo mass as a function of redshift. This is for the 11 clusters that we had Herschel-Pax data for. So we're summing up all the star formation here, and as a function of the halo mass, and we're comparing it to this black line and shaded region, which is the global relation for galaxies that are living in 10 to the 12 solar mass halos, which is kind of the peak efficiency, the star formation efficiency. That's where we expect it to be happening. And so you can see that there's quite a variation within our population of massive clusters, but on average, when you get up to this redshift 1.5 era or so, you're forming stars at pretty much similar rates as the more normal field galaxies that we think about. Okay, but everything that I just showed you has been for massive galaxies in clusters, because of course, to confirm, and to detect and confirm cluster membership for lower mass cluster members is pretty expensive. And so what we wanted to do next was try and push below what we've been able to do so far with massive galaxies and look at the rest of the cluster constituents. So this is the technique that I'm going to talk to you about, which is just a stacking technique, is not a new way to look at cluster populations. And it's recently had a resurgence in some protocluster studies. So this is a paper that came out in 2015 from the Planck collaboration. And they showed very nicely what you could do with a stacking technique. So this is over here, a Herschel Spire 350 micron stack of 220 protoclusters. So here we're not caring about where any of the individual cluster members are. We haven't had to confirm them or anything. We are just centering the stack on the cluster, the center of the cluster as well as we know it, and stacking them all together and then looking at the resulting extended emission. So the nice thing about this is that we are getting, in this case, the dust emission from all constituents, both the massive cluster galaxies that I was just talking about, which we've seen at higher redshifts can be doing quite a bit. And of course, at protoclusters, we found them to be doing quite a bit as well, but also the lower mass cluster members. And in this case, in the infrared, if there's any intracluster dust. So I put a little star, a little asterisk here to note that even though intracluster dust would be included in this stack, more dedicated attempts to detect intracluster dust have so far only found upper limits, and so we're not really sure. This component probably doesn't contribute that much because it's been extremely hard to actually find, and the upper limits kind of constrain it to being not that much of a constituent, but included there for completeness. And then if we go ahead and we expand this out to looking at multiple wavelengths, such as here, I'm showing work on protoclusters at Redshift 4 from Kubo et al. 2019. You can go ahead and you can start to play the game of constructing cluster SEDs and looking at different constituents of different properties of the total cluster constituent that you're now able to look at. So for our study, we chose first to start with the Iraq Shallow Cluster Survey. So this is a cluster survey that is in the 9 square degree Bootes field. This field is really nice because it has extensive UV to infrared, far infrared photometry. And from this, we were able to do quite a lot of work on the clusters already. They are selected from a 4.5 micron mass selected galaxy catalog. So we're basically looking for overdensities in stellar mass. And because we have full redshift probability distribution functions, we can identify the clusters as overdensities in stellar mass and then also identify cluster members using their photo-Zs by placing them in the cluster with some probability. So from the survey, we've identified over 300 clusters up to Redshift 2 or so. And then we've gone out and gotten a lot of multi-wavelength spectroscopic follow-up to confirm some subset of the clusters. And then also X-ray and weak lensing measurements and other statistical arguments tell us that this cluster sample has a mass of about, a halo mass of about 10 to the 13.8 solar masses, and that this halo mass is kind of uniform over our entire redshift range. Because of the way that we've selected the clusters as stellar mass over densities, it kind of just worked out that way. So if you work on clusters, you might be used to thinking about progenitor cluster samples, where you would have your higher redshift clusters would be less massive and they would presumably turn into your lower redshift clusters over time. That's not what the sample is. The sample is kind of a fixed mass sample, which is nice because it allows us to look at the same mass at different redshifts and kind of take that out as a parameter. Ah, yes, and I forgot. Okay, so this is this is an optical image of one of our clusters, and you can see that the optical image doesn't show you all that much, but when you go and look for the stellar mass over density using the 4.5 micron catalog, you overlay that, and the cluster pops out rather nicely. I should also note that the clusters that we did follow up with X-ray and whatnot, they have detected intercluster mediums, so they are well virialized and have that that hot gas, but they are also the ones we went after them because they were the most likely to be detected. So it's possible that not every single cluster in our sample is virialized and relaxed. There's most likely a mix, but they are all around this mass on average. Okay, so now what we're going to do is we're going to take our clusters, we're going to split them up into redshift bins, enough to get a good signal, and then stack them in order to obtain the total cluster emission. So here is just a nice graphic that I like to show illustrating the concept of stacking. It's a pretty straightforward technique, though interpreting the results can be somewhat complicated. But we are going to take cutouts around all of our clusters in our redshift bin, and then add them together in some usually weighted mean. And what this does is that it increases the signal to noise by the square root of the number of objects you put into the stack, allowing you to pick out a signal that might have been previously undetected in the individual cutouts. So we're going to do this stacking over multiple wavelengths because we want to look at different properties of the cluster. And then one of the things that we wanted to consider is that it would be really nice to expand this technique out to other cluster samples that have been selected in other ways and have different halo masses. And so we were really focused on the WISE data as an all-sky survey that can be applied to pretty much every cluster that we have found. But the nice thing about the Booties field is, of course, that we have other data as well. So we have WISE here, we have IRAC, both tracing the stellar mass, and then we have WISE, the WISE longer bands and MIPS, and then the Herschel Spire data that traces dusty star formation. And of course, it's really nice that we have some overlapping filters here. Some of the WISE short bands and the IRAC short bands overlap. And so we can check them against each other and assure that our stacking technique is returning something reasonable and that we can then go and apply to other cluster samples that only have WISE data. So one of the considerations when you're doing this kind of stacking is that you would prefer that everything that you're stacking be kind of individually undetected and distributed, with nicely distributed noise properties so you can interpret your stack. So one thing that we ran into when we were doing this was that, of course, the deeper data in the WISE and IRAC short bands has a lot of detected a high fraction of detected galaxies, both the foreground and background field galaxies, which will hopefully be taken out properly via background subtraction, but also a high fraction of the cluster members themselves are detected. Of course, that makes sense because we looked for these clusters using detected 4.5 micron sources. So we've identified previously all of the massive members in these clusters, which is nice because we can then look at our stacking technique and see what fraction of the stack is coming from sources that are beneath the noise level and what fraction is coming from sources above the detection limits, and kind of look at how you would have to correct to get the total emission in the case of data with this depth. And because we want to apply this to more cluster samples using WISE, it's pretty nice that WISE has kind of more or less uniform all sky coverage. So, you know, if you're looking at similar clusters to this one, but you don't have the cluster members already identified, you can kind of take a cue from what we've done here to, you know, apply a correction. And so that's what I'm showing down here in this table. We have 4 Redshift bins, which I'm going to talk about a little bit more in a minute. And we've looked at the, what we've done is in our stacking, we've masked out all detected galaxies in the WISE and IRAC data, but then unmasked the ones that are cluster members and compared the stacks where we unmask the cluster members to stacks where we leave everything masked, and to see what is the fraction of emission that is coming from detected cluster members versus the things under the noise. So you can see here that it varies as a function of redshift, of course. As you go up in redshift, the fraction becomes less, but at low redshifts, it can be pretty substantial in the 2 shortwave bands. And then the other thing I wanted to point out about our data, it's something that you need to be careful about, is when you're stacking on Herschel Spire data, which unfortunately is not all sky, but there are a lot of cluster samples that do have Spire data. You're going to have to worry about the large beam size, because if you think about it with your stack, you're stacking together. Involved with the beam size, it's going to take the cluster emission, it's going to artificially spread it out. And so we are going to talk about this a little bit in a minute when we talk about radio profiles. Okay, so as I said earlier, we took all of our clusters that were between redshifts 0.5 and 1.6, and we split them into 4 redshift bins. We only did 4 bins, even though you of course would like to have smaller bins. We only did 4 because we wanted to get a good signal in the stacks. So each of the redshift bins is stacking somewhat 40 to 80 clusters, I believe. This here is showing our redshift 1 to 1.3 stack, and these are, bin, and these are our stacks at every wavelength. So you can see that they are all well detected. The white circle here is the 1 megaparsec radius, which is approximately the virial radius for clusters with this halo mass. And you can see that it is not only detected, but it is also extended in all of the wavelengths, including at 500 microns, where we have a rather large beam, we still get extended emission from the cluster stack. So this means that we can look at the radio profiles and actually start to quantify what the radio profiles are doing at different wavelength regimes that represent different properties like stellar mass and just obscured star formation. So these are our observed profiles. You might notice right away that they kind of are pretty similar. They all fall off kind of around the same spot until you get down to, you know, the more far infrared wavelengths, where you start to see that maybe this is a little bit extended. And of course, as I just mentioned, the beam here is doing some work to spread out the emissions, so we're going to have to account for that. So in order to do so, we wanted to pick kind of a model to try and model these radio profiles with. So we picked the NFW profile. So the NFW profile was originally used to describe cold dark matter halos in N-body simulations. And it's since been shown to also well describe the stellar mass profiles of clusters for the most part, with a little bit of not describing so well the very center. But the NFW profile is pretty nice for our purposes because it can be parameterized as these two power laws with just this kind of scaling, this RS parameter between the two. And when you know kind of the virial radius of your clusters, you can take virial radius by the scaling and you can get the concentration. So the concentration parameter is nice because it is related to the halo formation time, such that halos that form earlier should be more concentrated. And the inverse of that is the more massive halos that form over more time are usually less concentrated. So this is the profile that we adopted to describe our, to try and fit to our observed profiles. And to do that, of course, we need to make some corrections to try and recover the intrinsic profile for our stacks. So to do that, what we did was we took the NFW profile as our fiducial model. And then we had to, the first correction is that we don't know exactly the centers of the clusters which we're stacking. So you can imagine that, you know, we tried to, the centers were determined for our clusters based on the wavelet algorithm that looked for the stellar mass over densities to identify these clusters. But of course, there is some uncertainty associated with the centroiding. That uncertainty is about 15 arc seconds. And so what we did was we drew centroid offsets for different realizations and convolved them with the NFW profile. So you can see that that kind of spread things out a little bit. And then of course we had to account for the beam size. So the beam size in the IRAC 3.6 micron is of course pretty small. So it doesn't, you know, have that much of an effect. But for the Spire data, at 250 microns, you have an 18 arc second beam. You can see that, you know, this takes the profile and spreads it out quite a bit. So if you take here, which has both the centroiding offset and the beam size correction, and you divide them back by the intrinsic profile, then you have the correction that you need to apply as a function of wavelength to your observed profiles. And you can see again that the Spire beam is really bumping things up, spreading this emission out over here. So this is what we did here. This is showing again for our Redshift 1 to 1.3 Redshift bin. We are showing the uncorrected radial profile at 3.6 microns here in the white points. And then the corrected profile, so this is 20 realizations with 20 different randomly selected centroiding offsets, 20 realizations of our corrected profile. And then here is the original NFW profile. And of course we went through and we fit this for multiple scaling lengths. So this is the one that fit the best, scaling length of 0.13. And you can see over on the right, the scale length, the chi-squared is of the scale lengths that we tried. And basically the scale lengths that are much preferred are these ones up here, which correspond to a concentration of 7 or so, so pretty concentrated. And the concentrations that are lower, which would be over here with the longer scale lengths, are pretty much ruled out. So this was nice to find, particularly because, you know, there aren't that many observations of clusters above Redshift 1 and with radio profiles in this way. We compare here in the gray triangles to the study from Vandenberg 2018, which was massive clusters of Redshift 1, and they also found a concentration of about 7. So that was nice to see. However, we realized quickly that we actually see this high concentration in all of our Redshift bins, which maybe is not surprising because our observed profiles were pretty similar in all of our Redshift bins. But, you know, again, we are looking at a sample that is uniform halo mass, So you might have expected that, the same halo mass at a later time might have a different concentration, but no, we find this high concentration. So this is maybe indicating that, the concentration for these stellar mass distributions is tracking the halo mass. And there is some evidence that for the dark matter component only, the concentration is a function of halo mass. So this is a study from 2013. You can see that there's a lot of scatter here, but they found, or they posited a relationship between the dark matter concentration and the halo mass. But of course, when you try to simulate this and you add in baryon physics, things get even more complicated. And if we go and we look at the literature for the concentrations that have been measured for pretty massive clusters at redshift 1 and below for the stellar mass component, you can see that there are things all over the place. So here is the Vanderburg study that I just mentioned, where they find a high concentration for clusters that are slightly more massive than our sample. But then you can go and you can find another cluster sample at the similar mass to theirs where they found lower concentrations. So this is telling us that we really don't understand what is driving the concentration in clusters at this point. But what's really nice is that this technique will be able to look at that in a more uniform way. Again, the WISE all-sky data is really great to be applied to many cluster samples, including cluster samples that have a much wider range in halo mass, unlike our kind of fixed halo mass sample. And then also another thing that might be driving the differences in the literature is the different selection techniques that are used to identify the clusters. So some of the clusters are identified as stellar mass overdensities, but others are identified via the SC effect or, red sequence selection techniques. So all of these things complicate what the differences that we want to get at from these different cluster samples. And so doing this via WISE would be a really nice way to kind of get around some of these open questions. The other thing that's nice about the stacking technique, other than the fact that it gets at more of the full constituency, is that stacking averages over substructure, which you might worry about, different substructures if you're looking at individual systems. But I put a little asterisk here again to note that, when you're looking at WISE and you have a high fraction of detected massive galaxies, particularly at low redshifts, you're going to need to account for that when you're doing this total emission. So we went ahead and we fit the NFW profile to the dust emission as well. I'm getting a note that my internet connection is unstable. Hopefully that holds. So we went ahead and we fit the NFW profile to the dust emission as well, which didn't need to work, but we actually did find that it was a decent fit to the far infrared profiles with similarly high concentration to the stellar mass. But with this little caveat that it doesn't quite work in the center. So here we are showing the radio profiles again. The red points, or the red line, is the 3.6 micron stellar mass profile convolved with the Herschel Spire 250 micron beam. So now we're taking out again that effect of the beam size spreading out the emission, and then we're comparing it here to the open circles, which is the 250 micron stacks. Radio profiles, and you can see that we're missing some emission in the center, and this is down here again, this is the ratio of the two, and we're missing emission, far infrared emission, in the center of our clusters at pretty much all redshifts. So this was a bit of a surprise, considering that we found that the massive dusty galaxies in these clusters at this highest redshift are maybe starting to be less efficiently quenched than they are at lower redshift. But this is showing that when you look at the total emission, there is still some environmental effects that are happening in the very cluster cores at all redshifts. So to try and get at that a little bit and to look at more general properties of the clusters, we went then from the radial profiles which show us that most of the mission is within the virial radius or so, which is about 1 megaparsec, to measuring the total integrated emission, which again includes the massive cluster members, the low mass cluster members, and any intercluster dust component that might be there. So this is again just showing some of our stacks, this time in the different Redshift bins at a couple of select wavelengths, and this is showing the 1 megaparsec radius. And you can see that, yeah, the emission is very concentrated, but of course it does fall off all the way out to here, and then so we use aperture photometry to get the total integrated emission, and constructed total cluster light SEDs. So this is the SED for our lowest Redshift bin. Oh, I need to go a little faster. This is the SED for our total cluster emission for our lowest Redshift bin. The points that we used in the SED fitting are the closed red points, and the best fit SED is the red line here. You might notice that these points in the middle are open. That's because we didn't use them in the fit, which is of course missing PA emission. You can see that here. And the reason is because recall that our Redshift bins are pretty wide. This one is from 0.5 to 0.7. And so, you know, when you have these very complex PA features in that regime over that Redshift, you're kind of going to, you know, convolve a bunch of different Redshifts together and smear that out. And so we decided we just would take that part out because it was pretty complicated to model, and instead just fit these other points. And for comparison, we have the black line here. This is a star-forming field galaxy, and in an infrared bright star-forming field galaxy from Kirkpatrick et al. 2015. And in the green points here, we have the Planck clusters, which is another stacking analysis that was kind of the closest in Redshift to what we had looked at, and we were pretty excited to see that this, you know, agrees pretty nicely. Another one other thing that we did was we looked at the far infrared emission in a 2-temperature model. So this is the cold dust component and the warm dust component, and I will come back to that in a minute. Okay. So now this is all of our SEDs over our 4 Redshift bins. You can see that they're kind of all somewhat similar. There's definitely a big difference over here between the you know, the high mass IR bright field galaxy and our cluster emission, and a little bit less difference over here. And then, okay, so first I wanted to start with talking about the near infrared emission, however, so we can derive from this the total stellar mass for our clusters. And model predictions are that the stellar mass to halo mass ratio should be 1 to 3%. So recall again that, you know, we have this kind of average halo mass here. And so we plotted up the stellar mass to halo mass ratio, and we find that it is in the 1 to 3%, albeit with pretty big error bars. So these are the simulations showing what the predicted values are, which we are consistent with. And the nice thing that you can do with that is you can look at the stellar mass to halo mass as a function of halo mass. And there's some tension here between the models and the observations. So these are showing the models for Redshift 1 and Redshift 0 from some recent simulations. This is a Redshift 0 observed relationship, and these are some individual clusters, and you can see that there's, you know, kind of some tension here between what the models are predicting and what the observations are showing. These here are our clusters, which unfortunately with our large error bars weren't able to distinguish between these two models, but you can imagine applying this technique to more cluster samples and starting to get a handle more on you know, how this tension breaks down. So one of the things that also we are starting to do now is you know, bringing down these uncertainties by adding in UV Galax stacking. The UV Galax stacking traces the young you know, the young ongoing star formation, which we are currently missing from our stellar mass estimates. And so that'll really nicely bring some of these errors down. We might be able to take a closer look at this. Okay, so going back to the SEDs, We'll look beyond the stellar mass part to the far infrared. And what this is showing us here, this difference between the infrared bright field galaxy and our SEDs, is that there's a lack of warm dust. And this lack of warm dust is characteristic of lower mass galaxies. And so using our 2-temperature model, we looked at this a little bit closely, the ratio, a little more closely, the ratio of the cold luminosity to the warm luminosity from these 2-temperature fits. And you can see that, this is the field ratio, particularly at our lowest redshifts, we deviate from this quite a bit. And one thing that was interesting is that the recent stacking on protocluster samples at Redshift 4 kind of shows the opposite. So we are lacking in warm dust. They showed an abundance of warm dust, which they attributed to AGN. So, expanding these stacking techniques to more samples can maybe figure out, where this transition is happening. But does it make sense that our, SEDs are dominated by maybe lower temperature, low mass galaxies? So to look at this, we took our known massive cluster members so that we have previously measured the star formation in our massive cluster members. And so we can compare them to the total emission stacks that we've been doing in this study. And so what we did was we took the 250 micron and stacked the individual, now we're stacking on individual cluster members that have been identified via photometric redshifts in 2 mass bins from 10 to the 10 to 10 to the 11 solar masses and above 10 to the 11 solar masses. And when you do this, there's a lot of things that you have to worry about with details in a previous paper that I've worked on. You have to correct for flux boosting, and you also have to correct for field contamination due to using photometric redshifts to identify your cluster members, which is only so precise. You're going to have some field contamination in there. So there's some corrections you have to apply, but then once you've done that, you have the total emission from massive cluster members within the virial radius, and you can take that corrected, normalized by volume, and get the infrared density, the infrared flux density of massive galaxies at 250 microns divided by the total that we've from our total cluster stacking. And so this is kind of going to give us the, the contribution from massive galaxies to the total. And to, have a comparison for that, I went and we gathered some field comparisons. So we have 2 field comparisons, first from K-band field catalogs from Vero 2018, where they did 250 micron stacking on mass limited cluster catalogs. And then also from the SIDE simulation, which is a simulation of dusty star forming galaxies. Okay, so when we look at this ratio or this contribution from the massive galaxies, the massive cluster galaxies only to the total, let's look first at the high mass bin. So this is galaxies with greater than 10 to the 11 solar masses. Here in orange are the cluster galaxies, and here are our field measurements. The observed field measurement is here in this hatched region, and the SIDE simulation gives us this orange region down here. So you can see that for our most massive constituents, the cluster and the field galaxies are contributing approximately the same to the total stacked infrared emission. But when we look at the more intermediate mass galaxies from 10 to the 10 to 10 to the 11, we see a remarkable difference between the clusters and field. So here again is the observed field up here in the hatch region. This is the simulated field from the SIDE simulation. And our cluster galaxies are these purple points way down here. So in total, it seems that, from our total emission stacks, galaxies that are greater than 10 to the 10 solar masses in clusters are only accounting for 30% of the cluster emission at 250 microns. So they're only contributing, a relatively small fraction of the infrared emission that's going on in these cluster systems. So that's consistent with what we found in the SEDs, that they're dominated by these low mass cluster constituents, and particularly at the lower redshifts, although we find at high redshift that these seem to be a low fraction as well. And then, okay, so keeping that in mind, we're going to switch tacks slightly and then look at the total obscured star formation rate that we derive from our far infrared bump. So here we are looking at the specific star formation rate as a function of redshift. So here in the red points are our total emission stacks as a function of redshift again, and this is the green points are the massive galaxies only. The line and the open green points are from previous studies, so pay attention to just the squares for now. The red points, the total, blue points are the more massive galaxies. And you can see that they kind of follow a similar track. So we were finding earlier that massive galaxies in clusters kind of have, approaching field-like star formation rates and specific star formation rates at high redshift, followed by this decline, this increase in environmental quenching efficiency, as we saw in this other way, in this other study. And the total cluster emission, which again is dominated by the low mass galaxies in the infrared, is also following kind of this track. So here in the black line and the shaded region is the field relationship for galaxies around 10 to the 10 solar masses. And up here at this highest redshift, we see that we have field-like star formation, again, followed by increased efficiency. So it would seem that, at redshifts less than 1.5 or so, the environmental quenching that we saw operating on massive galaxies and ramping up at lower redshifts is also acting on the low mass cluster constituents. Okay, much time, all right. Okay, so now that I've showed you these two things, that we have kind of field-like star formation activity happening, throughout the cluster populations at higher redshifts, but also that, there's a big discrepancy between the field and the clusters in terms of what kinds of galaxies are contributing this star formation activity. I wanted to ask the question, what is providing this field-like star formation up here if it's not the intermediate mass cluster members that would be providing it in the field? And of course, if you're familiar with, dusty studies of galaxies, when you go to lower masses in the field, and this is a paper from Whitaker et al. 2017, when you go below our 10 to the 10 solar mass limit here, the fraction of the star formation that's obscured drops pretty rapidly. So you get to these lower mass galaxies that are presumably dominating our cluster emission, and you don't expect them to be putting out a lot of, having a lot of output of obscured star formation activity. So I just we'll go through a couple possibilities for what might explain this discrepancy. The first is that, maybe the high mass or intermediate mass cluster galaxies quenched early, and the low mass the cluster galaxies are all starbursting. Well, of course, this is probably not true. We've seen in these, studies of high mass galaxies that, the high mass galaxies at redshift 1.5 are still undergoing quite a bit of dusty star formation. And also when we do try to push down in the cluster populations to lower masses, we don't suddenly see that, the lower masses are starbursting. They're usually on the main sequence, although of course we haven't been able to push down to, extremely low mass cluster galaxies. It gets very expensive. The second possibility is that we just have a different ratio of low mass to high mass galaxies in clusters relative to in the field. However, this has not been found, at least in the relatively massive cluster populations. This is a recent study from Vandenberg et al. 2020 that looked at the go-green clusters. This is the stellar mass function, and they were able to do this because the go-green clusters have quite a bit of spectroscopy to identify members, so they could split their populations into star-forming and quiescent cluster galaxies and look at the stellar mass function relative to the field stellar mass function. And even though these plots kind of look different, they found that the shape of the stellar mass function between clusters in the field was very, very similar. And the thing that's changing is down here, the quiescent fractions versus the field. Of course, these clusters are quenching more galaxies faster than the field, which makes sense with what we know, but kind of rules out that we have, different ratios of low mass to high mass galaxies, even down to 10 to the 9.5 or so. And then the last possibility that we entertained in the paper, which is kind of my favorite, but we don't have a lot of evidence for it, is that cluster galaxies may be more dusty than their field counterparts, particularly if the low mass cluster galaxies are more dusty than their field counterparts, then maybe they can start to make up some of this difference that we see here. But this is not something we've been able to look at very closely yet. Of course, confirming low mass cluster galaxies is hard enough. It's even harder when they're dusty. So this is something that's kind of future work. But we do have maybe a hint of it. So this is a study from Hatch et al. 2016. And they were looking at kind of a cluster region at Redshift 1.6, where there's kind of the massive cluster core, which they call the massive group, and then kind of the surrounding regions, the intergroup regions. And they were looking at the fraction of red star-forming galaxies in these two regions. And they found that the fraction of dusty sources in the massive group area was higher than in the surrounding areas. And then when they, but of course, this is a function of mass down here. So you're saying these two lines are parallel, so there's not that much mass dependence. But when they corrected for their completeness as a function of mass, they estimated that, maybe this line could actually be, more a function of mass in this manner here. So this is something that is, open work, but it would be an intriguing way to solve kind of this dilemma that we've uncovered in some of our data. So what do we do next? So of course, we're going to do more stacking, as I've said throughout the talk. It would be great to apply this to as many cluster and protocluster samples as possible. Everything's covered by WISE. A lot of things are covered by Herschel Spire. Everything's covered by GALAX as well. And as I mentioned earlier, getting at the unobscured star formation component and getting better stellar masses by constraining that young population with GALAX is one of the things that we're now working on. We want to look at more samples that have a range of halo masses. So over here we show, this is a plot of the halo masses of the MADCOUS clusters. So the MADCOUS clusters are identified as overdensities in WISE, and the contoured region here shows you that there's quite a range in halo mass in this sample. So you can really start to look at things as a function of halo mass. And then I also wanted to point out that the large millimeter telescope in Mexico will have a 1 millimeter camera called Toltec coming up that will be able to do large surveys of submillimeter and millimeter emission to get at the gas and dust and start to see what the total dust emission looks like in these clusters as well to address some of the things that we brought up here today. Okay, so yeah, all right. That's my summary slide. I'm just gonna leave it up there and I'll take any questions.
Thanks, Stacey, for a really great talk. So now is the time for our Q&A session. We're at the top of the hour, but I think we can hang on for a few minutes to ask Stacey some questions. So if you have questions, please type them into the Q&A, not the Q&A, please type them into the chat window. And then I will moderate the questions to Stacey. And while people are thinking, I will go ahead and also just announce that we have these webinars monthly on the first Tuesday of every month at the same time, 1 p.m. Eastern, 10 a.m. Pacific time. So our next webinar will be in November on, I think, I have to look up the date exactly, but stay tuned for our future webinars. And we're always looking for speaker suggestions. So if you yourself would like to give a webinar, or you know someone who would give a great talk, please do contact any of us on the Leadership Council with your suggestions. We are especially interested in featuring speakers, early career speakers and speakers from diverse backgrounds. So keep that in mind in the future. You just explained things too clearly, Stacey. Oh, here's a question from Alex Pope. Can you comment on the prospects of JWST for studying clusters or protoclusters?
Yeah, so I mentioned at the top of the talk that we are going to be looking at some local galaxies that are falling into clusters, random pressure stripping happening to them. And so there we're going to look at the shocked H2 gas through the JWST MIRI medium resolution spectrograph. And so we can really start to look at, you know, what's happening in the tails. We're finding that there's a lot of star formation that's happening in the tails, and one of the open questions is whether that star formation is happening from gas, you know, that directly stripped from the galaxy, or if it's gas that kind of recollapsed in the tail itself. And that'll tell us a lot about how effective ram pressure stripping is at actually quenching galaxies as, you know, an environmental mechanism of quenching. There are, you know, going to be, unfortunately, JWST is not very good at doing particularly wide surveys, so it will be mostly good at looking at, you know, individual clusters and individual cores. But, you know, with the things like NIRCam, you can get a lot more near infrared imaging, and you can do a lot better with like photo Z's and such. So it makes it a little bit easier to identify cluster members and look at some of their properties. And, you know, with higher resolution, such as with MIRI, so we would be able to improve on the you know, Herschel and some of the Spitzer observations that we've done in the past.
Great. Okay. If anybody else has any questions they'd like to ask, you can type them into the chat window. Otherwise, I think let's thank our speaker again. So thanks to Stacey for a wonderful talk. Please join us at future IR SIG webinars, and have a wonderful week, everybody.
Thanks, everyone.
Thank you.